So very good revisions. If I ask you how you will determine whether two protons or two hydrogens or something more, something similar kind of groups have homotopy relationship or not, then what you will do? You just replace one atom by something another group, let's say Z, and you find that whether upon two consecutive replacement the two molecules are same or not. If these are same, then they are homotopic. So, and other things that, so basically just I am not going to discuss more details in homotopic, just rotate the molecules, and if we end up the molecules same things, for example, uh, we have two protons, let's say two hydrogen, replace by, you can say it's real or imaginary, anything you can do, imaginary group. If you do this, you will end up with two molecules. Let's say this is 1, this is 2. And if 1 and 2 are interconvertible by rotation, then 1 and 2 are same molecules. Okay, so basically what? The homotropic molecule is the same molecule. So the homotropic protons or hydrogen atom have same chemical environment. This is the statement you should always remember. That's why they will appear on the same ppm values. Okay. Now I will tell the term of chemical environment, or so what is mean by chemical equivalence. So the let us write here. So homotropic hydrogen atom has same chemical environment. Atom have same chemical environment. Okay. Now we'll ask, sir, what do you mean by same chemical environment? How we can think that whether these two things are same chemical environment or not? That we are going to discuss just shortly. So just before that, as they have same chemical environment, they will appear on same ppm value. They will appear on same, not ppm values, deltas values in ppm. That's the nature of homotropic protons. So now, if it has been asked by question that these two signals will come together or come in different places, then we have to judge the topicity relationship, whether they are homotropic or something not. Now I come to the point, these things. What do we mean by same chemical environment? Let's say we have two nucleus or more than two nucleus that can be related by a symmetry element like center of symmetry or plane of symmetry. That's why, let's say, okay, definitely we'll just explain this in terms of examples. Let us just discuss the statement first. So we have two or more nucleus, means carbon CH3, this kind of things. Okay, so nuclei, if they are related to each other by symmetry operations, which kind of symmetry operation? Sigma or I, that is plane of symmetry or the whatever. Let's say just write it here in terms of this symbol. So plane of symmetry plane of symmetry or axis of symmetry. Then, if they are related, by, this is very much fundamental and interesting and easy to just nothing remember about that. Then they are said to have, or they are supposed to have same chemical environment. Same chemical environment. Okay, so you may think that okay, this might be quite complicated. What are the things? The two or more nucleus, and they are related by the symmetry element. What is that? It's very simple. Now let's have example on that. We have, let's say, this methyl group and this methyl group. Now I am asking you, are these two methyl group have same chemical environment? Then how will judge? Just apply this. Let's think whether they are related to each other by symmetry element sigma or not. Think this molecule is placed on the your device screen. Then if you have a plane perpendicular to this device screen, then see this is the sigma point. So this is the thing, mirror image kind of thing, sigma. And let's see if I put on axis on this screen also. This is sigma, and this is the axis of symmetry. See, these two methyl groups are just mirror image through this plane, and just axis just apply on C2, they will be same. That's why these two methyl group are same chemical environment. So two methyl group has same chemical environment. So now what we learned up to this, we are trying to see whether the homotropic signals appear at same places or different places. Now we understand homotropic atoms, same chemical environment, hence will appear at same delta value in ppm. So basically in organic chemistry, normal what happened, you cannot get repeat questions. Basically what we should do, we should have crystal clear understanding. So that the question comes from that any angle, we can tackle the questions. That's why we are doing that much crucial discussions. Okay, so this is the case of homotopic. I will take more example today for homotopic and something. Now let us think about the example that I already given. Let us do the replacement by okay. If we have already done that part, we will not put that much amount time on that. We'll take some another examples. Yeah. So we have, let's say this is CH3 Cl, and this is, let's say, HA, this is HA, this is HB. So they are asking, so how the signal will come for these 2A? They will come at same ppm values or different ppm values. Now we'll apply the replacement theory. Just apply replacement. Replace 2HA by Z 1 by 1. Then we'll end up with two things. Here CH3, let's say this Z, and this is H. Now we have HB, HB, Cl, and here CH3, let's say Z, H, 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 Cl. Think this is 1 and this is 2. Look, basically, if you turn the molecule just 180 degrees, this will convert it to 2. So basically, 1 and 2, same molecule. Means, now we are writing that Cl, H, H, these two H are homotopic, and if they become homotopic, then what will happen? It indicates that we will have same chemical environment, same chemical environment, and same delta value. Delta value. Now we'll say the concept of enantiotopic. Enantiotopic. So for enantiotopic, what? The same thing. If you have two molecules, let's say we have been told about two protons. Think about these are the molecular entity, and I have two protons. Then replace by Z, we'll get two things. Now see or check 1 and 2 is mirror image or not. Is mirror image or not. If they are mirror image, so they are enantiomer, means these protons are anisotropic in nature. If they are not mirror image, then something we have already discussed that they may be homotopic, they may be diastereotopic, but now we just will be here locked about the anisotoxicity. So if they are mirror image, they are anisotropic. So what will be case the for anisotropic protons? So basically, how we can get a clue? Let's say we have a carbon atom H, we have two protons. They are asking whether they will be homotopic or anisotropic, diastereotopic. We'll just look the two different group. If the carbon nucleus have two different group R1, R2, then normally these two protons normally are said to be are anisotropics in nature. Okay. Then what will happen for anisotropic? Now we will take it by examples. Anisotropic protons have same chemical environment. Look, the anisotropic, their chemical environment same because their neighbor are same. As their neighbor are same, just they have similar chemical environment. Okay, so they are similar chemical. Anisotropic hydrogen have topic hydrogens atom has same chemical environment, means same delta value. That's why if the question is asked, the anisotropic hydrogen can have signal into different places, that is wrong. We cannot detect the anisotropic protons by NMR spectroscopy. These appear in the same ppm value. So, enantiomic hydrogens or protons cannot be detected by NMR. Very fundamental. Anisotropic H atom cannot be detected by 1H NMR. NMR. But there is a way out also. But is it absolutely right? The enantiotopic protons cannot be detected by 1H NMR? Not. It is not absolutely right. Enantiomeric protons also can be detected by NMR. So this is a very strange question. Now we discuss they have similar chemical environment. How we can detect by NMR? There is two route. One route is that modify the molecules by some diastereomeric invariant. Number two solution is a very fantastic solution. Use one chiral solvent. So when we'll what later you will NMR spectroscopy we see that your molecule have to be or has to be dissolved in a solvent. If that solvent is a chiral solvent, then chiral solvent will provide chiral environment. Very much fundamental things. Chiral solvent will provide chiral environment. In presence of this chiral solvent, particularly the chemical equivalence or chemical environment will be different. Then we'll have two signals. So if somebody asks about that, okay, not so many protons can be detected by NMR, there will nothing, no need to just worried about that thing. So we have to read something very fundamentally, very carefully what is written there. Normally, like homotropic, enantiomeric protons or atoms, hydrogen atoms have same chemical environment. We cannot detect them by NMR. But look at the solvent. If the solvent is chiral, that particular chiral environments provide different chiral chemical environments. As a result, they can be resolved. So here, after this kind of discussion, if there is a just written questions, just without asking any solve the structure, just only written statement is there. Whatever the statement tough or something, we can easily rectify the what they are trying to say. So what we learn? Homotopic proton cannot be detected. Anisotropic proton. If you use chiral solvent for homotopic proton, nothing because only one molecule is there. No two molecule is not there. Nothing will happen. So homotopic proton not detected by NMR. Use chiral solvent, nothing will happen. Anisotropic protons is not normally detected by NMR, but add one chiral solvent, a chiral environment will be generated, and we can detect them by NMR. That's the thing we have learned up to this. Okay, let's say we have these things. CH2, CH3. Now, there is a question. Let's say it has been asked that whether this two proton will appear in the same region or different region. In the same region or different region. They didn't mention the solvent. You know the answer now. Now you just have a rough calculation. Let's see. Okay, let's see how the molecule looks like. You put CH3 here. Now put one C6H5. This benzene. Now we have these two protons. Also, you know the replacement theory. Apply this replacement theory. CH3, C6, H5. Let's say Z hydrogen. Here CH3, C6, H5, Z hydrogen. Let's see, it is 1 and this is 2. So they are mirror image relationship. Put one mirror here. If I put one mirror here, so what I am going to get, I have CH3 here. This is C6H5. I will have H here and Z is here. The same thing means 1 and 2 enantiomer. Enantiomer. As 1 or 2 enantiomer, this CH2, these two protons, same chemical environment, same chemical environment. Hence, it is not detectable by the two proton is not distinguishable. We will get only one signal. Only one signal. Then, here, if the protons make a diastereomeric, if the proton are diastereomeric, they will have different chemical environment. Diastereomeric proton or diastereotopic protons. Diastereotopic protons. Simply, they are diastereomer. They are two different molecules. So they will have different chemical environment. Different chemical environment. So for that we will have two different signal. So up to this, what happens if we have CH2 proton in the same carbon? Normally, unwillingly, our mind go to in such a way that okay, we are going to get two carbon, sorry, these two protons together in the same places. Unwillingly, our mind normally goes there. But be alert that if the protons become homotopic, they are okay. If the protons are anisotropic, they are okay. If they are diastereotopic, they will come at different places. So normally, same hydrogen atom on the same carbon atom doesn't demand always to appear together. See these examples. So let's say we have these things: C double one C H H. We have Cl H H. If you have asked that whether these two protons are appear on the same delta values or different delta values, just do simple thing. So what to do? We have to see whether they have topicity relationship there. Then just go to the replacement theory. If I replace them, so let's say this Z H H Cl and we'll have H Z H Cl. Basically, it is what? This is trans. And this is what? This is cis. So cis and trans, they are two diastereomer. So these two protons have different chemical environment. They will appear on different places. So these two protons will appear in different delta values in ppm. So two proton in the same carbon means they are always appear on same value. Is not here. It appears on same, but for this case they will appear on different. Okay. Okay. I hope, not I hope, I strongly believe those you are attending the class continuously from the beginning, you are enjoying a lot, and also just hold your patience. Also, you'll enjoy a lot of new things, even much more better what you have learned now. That is coming just the next couple of minutes. Here, a lot of things to be discussed, but again, we don't have time. We will ask for assignment, do their job, and particularly after this class, we will have one dedicated class for solving the structure. That how we are applying all the things together. They will have one dedicated class. Until now, unless I discuss all things, I cannot discuss it now. Now, let's say a question has been asked in that way. This is CH3, CH, H, Cl. Now I am asking, are same delta values? Now you are expert to solve this. Okay. There is one tricks I will tell later. Now let's solve it rigorously. Now identify four groups. So at least this is one, two, three, four. So look at the group different. This is CH3, CH, and okay. Uh, okay. Just one Cl will be there because yeah. Let's Cl, and this is 2H, HCl. Now, what's our target? As the problem is that whether these protons is in the same ppm values or different ppm values, now we have to see the topicity relationship between these two protons, whether they are anisomeric, diastereomeric, homotropic. So I will go to the replacement part. If you just imagine the molecules by rotation not replaceable and just go to one replacement things. Here we are doing workout, but wait couple of minutes. I will show you the tricks which doesn't need this kind of workout. Let's say this is Z and this is HCl. We will have another things C3CHCl CZHCl. Put one mirror here. These things has mirror image relationship. Z inside Z, H, but this is not. So as a whole molecules, if this is 1 and 2, not mirror image. Mirror image. If they are not mirror image, then they are diastereomeric. So these two protons are diastereomeric in nature, or diastereotopic in nature. Always see the topic, don't say diastereomeric, diastereotopic. It's my slip of mind. I'm sorry for that, but it's diastereotopic. Diastereotopic in nature. So they have different chemical environment. Different chemical environment. If different chemical environment, then you will have different values. Now you come by previous examples. So never think that as this is CH2, this CH2 will come together. For these CH2, CH3 means ethyl benzenes, these two protons, same delta value. They came together. But for this thing, CH3, CHCl, CH2Cl, they are coming at different delta value. So be alert about that. Huh? Never think in mind that that is CH2B. CH2 we are going to get a lot of delta values. And these kind of things during my research work, I observed a lot. This is happening everywhere. If you have a raster environment, you are going to get different delta values. Okay, good. Then just I will stop these things here. Just topicity and NMR.